All right, we're going to talk today about dilations, which is our fourth and final transformation. So, dilation is a transformation that expands or compresses a figure. So it kind of goes without saying, this is not rigid, because if we can see here, we have a pre-image and an image. They are not the same size. One looks like maybe twice as big. So a rigid motion preserves shape and size, but this just doesn't. So it is kind of unique among our four. So if the scale factor is bigger than 1, like it is up here in this picture, we call this dilation and enlargement. And if it's between 0 and 1, so a proper fraction, then the dilation is a reduction or a shrink. Okay. So if we look here and say, is this dilation, enlargement, or reduction? So we're going from black to blue here because E goes to E prime and F goes to F prime and so on. So the blue is a lot smaller, so we're going to call this a reduction. And if we want to find this scale factor, we need to look at how lengths changed. So for example, EH is multiplied by a scale factor to get E prime H prime. Basically, old side multiplied by a scale factor, it gets new side. But this is 8, and this is 2. So N should be 1/4, or 0.25. Okay, so that's the scale factor. And in dilation notation, we choose to write it like this, which follows what was up here in this top picture. N is the scale factor, and C is where you're dilating from. Okay? So same thing here, black to blue, we see that that black triangle got a lot bigger. This is an enlargement. And for scale factor, again, look at how one side is changed by N. It became 4, I'm sorry, it was 4, and it became this whole length here, which is actually 12. So in this case, N is 3. Okay. Dilation notation, we would again say it was scaled by 3 around the center of dilation, which is X. So it's kind of like rotations. It has a point of interest there that we perform the transformation around. Okay. Let's take a quick look here. I'm going to just copy down the coordinates, so don't mind me. I'm just going to put these in here for you, and then we're going to talk about the pattern we notice. So going from A to A prime, how did we change? We went from -1 to -3, and also went from -1 to -3. So if you ask me, it seems like we multiply by 3. And we actually do the same here. 1 times 3 is 3, 2 times 3 is 6. So when we perform a dilation centered on the origin, we multiply the pre-image points by the scale factor. In this case, it was 3. And we can see that up here in the notation. You can go ahead and plot AB. And it says perform a dilation with a scale factor of 2 around the origin. So what I like to do is just copy down the points. So A goes to A prime. We know that. And we know that the scale factor is 2. So I'm just going to take the old points, multiply them by 2. Take the old points, multiply them by 2. And then, let's make these something else, like green. Uh-oh. Gets a little closer. So we have these 2 points now. And connect them. This is A prime, B prime. So we see that the line segment got twice as long, right? Yeah, it got twice as long, and we can see that shown in the points, and we can see that in the picture. So for our dilation around the origin, the coordinate rule is take your old point and multiply it by your scale factor. Okay? Let's do this for a triangle. So first I want to copy down the points. T prime, S prime, R prime. And now I'm going to also graph the preimage. Okay, this is R, T, S. All right, scale factor is what? It's 1/2. It's right there. So all of these points here I'm going to cut in half. Even numbers are easy to cut in half, but we have an odd number down here. But it's just going to be minus 2.5. Make this a different color. Plot those new points. R prime, T prime, S prime. Done. There's no more questions. So that's how dilations work. It's all about that scale factor. If it's around the origin, you can just multiply or divide the numbers as you see. Okay? So here's some just little word problem scenarios. Remember, just like we used the formula already up here. You take the pre-image, you multiply it times the scale factor, and you get the image. So that's what this boldface thing is talking about. I always search for the scale factor if we can find it, which is 40. So I know the structure of this equation I'm going to get. Something times 40 equals something else. It says that the microscope shows you an image. So what we're viewing on the microscope better match, right? If it says that the microscope shows a cell to be 2, and this is the image, and this is the pre-image, the microscope's image is 2. So just being careful to find those words, because it could be confusing. Does the 2 go here, or does it go here? Right? But we know that the microscope takes something that is really small and makes it 40 times bigger. So, in fact, this is going to be the formula we want to solve, which ends up being 0.05 millimeters. So this tiny ant, we put the microscope on it, we performed a transformation and made it 40 times bigger. Okay? Here we have a document that is 20.4 high, and we perform a zoom setting that makes it 25% as tall as it was before. So n, the scale factor, is going to be 25% is 1/4. Okay? So again, we have to take the pre-image, scale it by 1/4, and get the image. So the new image looks to be the unknown. What's the height of the new image? Well, if you don't know that, better call x. And the pre-image is what the height was before the change in the zoom setting. So this should be 20.4. And this turns out to be 5.1. So we can imagine like doing something like this, and this would be 5 point. So the 25% zoom scale kind of shrinks it down so that the height is 1/4 the size as it was before. All right.